Looks like we can get started. Welcome back, folks. We're now in week 6, and either the weeks are flying or they're going really slow, just to kind of depends on your perspective, I guess. For today's class, we're going to be starting out section 6.2. We looked at it just a little bit, a couple minutes at the end of today's class. So now we're returning to it in earnest to start working through this material here. It's a bit of a longer section, so this one we'll probably finish off when we come back on Wednesday's class. But any questions at all so far with the announcements? Okay, other announcement is just kind of scrawled over here in the black ink. We'll talk a bit more about it on Wednesday's class. Our exam 2 is now 2 weeks away from today. So that means on Friday, I'll be doing the task of going down here, putting down the firm sections that we're going to have on our second exam, put down below the documents for exam review problems you have to take a look at. And that's going to be my task on our Friday's class. After I do that, then I'll return to the grading and get these sets sent back to you as soon as possible. But welcome back, everyone. I think that's pretty much all of the announcements I had so far today. Any last questions before we jump in? Okay, well, here's where we left off. We jotted some things down, but I felt like it was a good idea to just erase it and start over fresh so we can get a good fresh look on how to graph the cosecant function. First thing we want to do is relate it to the sine function. And this is the kind of cool part about section 6.2, is that we know how to plot sine and cosine based off what we did in the last section, 6.1. And we're really just using that information to launch off and plot cosecant and then secant. So in other words, these same techniques from the last section carry over directly, and it's pretty remarkable. We plotted 5 points using the information here. We'll plot another 5 points and then just do a cosecant curve rather than a sine curve. So here's how we're going to start out. Main thing we want to plot is cosecant. First thing we should do is relate it to sine. We can say that y equals cosecant x is nothing but a 1 over sine x. Let's put that one in green. And from our training in algebra, we know whenever you have a fraction like this, particularly when x is in the denominator, you can potentially have vertical asymptotes whenever the thing in the denominator goes to 0. So this will have vertical asymptotes. When sine x goes to 0. Here we can relate that directly to the unit circle. Sine x equals 0 implies x is either equal to 0, positive or negative pi, positive negative 2 pi, and this list just keeps on going. It's an infinite list. Any multiple pi, odd or negative, odd or even, positive or negative, so we can go plus or minus 3 pi, plus or minus 5 pi, and dot, dot, dot to just say this pattern continues forever. So this will be helpful information for us. Now, next thing we'll do to plot the sine curve is do something slightly different with our axes, where we'll use the amplitude from sine. This is positive 1. And we want this to be a scale that goes a little bit more like this. So positive 1, negative 1 are way down there. So we used amplitude as 1. Next thing we can use is that the period is 2 pi, but we have to know where to get all the useful information. That's 1/4 of the period, or 1/4 of the cycle, or 1/4 period, which is pi over 2. So that's our unit length we plot across the x-axis. The sine curve starts at 0, right here. That's the x equals 0 part. Then when we go a distance of pi over 2, it hits its maximum. Things from section 5 or chapter 5, sine pi over 2 is 1. So we ought to label that. So here's pi over 2. Then out at pi, we're back to the x-axis. We have another x-intercept, so we're on positive pi here. 3 pi over 2, let me make that about the same length. 3 pi over 2, we hit our minimum down here, and now at 2 pi. or back to the x-axis for the next x-intercept. But these are asymptotes, so when we go to plot these, we'll have asymptotes that go like this for the cosecant function. Now we're about ready to plot, starting with the sine wave. It's just a nice gentle curve that goes along and about like that, not plotted too nicely, or too perfectly rather, I should say. But here's y equals sine x. Now, next thing we can do is start plotting the cosecant function, but really it's kind of looking at us. We started with the vertical asymptote because that's where we intersect the x-axis on sine. At pi over 2, if you calculated cosecant pi over 2, this would be just 1 over sine pi over 2. Sine pi over 2 is 1, so this is 1 over 1, and we just get a 1. So that just means right at pi over 2, both the sine function and the cosecant function, they just fully intersect. And these are vertical asymptotes. Our curve is attracted to the vertical asymptote, so it's going to move off and to the right in that way. It's repelled away from the x-axis at the same time. And so this is the first part of the cosecant function. We can't plot a point on the vertical asymptote, it's undefined. Cosecant pi is undefined, cosecant 0 is undefined. And if we use the same trick here, cosecant 3 pi over 2, well, in terms of sine, that would have been a -1. So this is -1 as well, and it does the same sort of thing. It's repelled away from the x-axis, moves downward like this, and like this. It's also at the same time attracted to the vertical asymptote. Let me try once more on that curve. And that's the whole thing. This is the graph of the cosecant function. So it tells us fundamentally, if you want to graph cosecant, it's in 2 parts now because of those asymptotes. But all you need to do is pay really close attention to how cosecant's defined and use our prior knowledge of the sine function itself. Well, any questions at all, folks, with the plot so far? Okay, this tells us a lot of information. First of all, notice that this right here and this right here would just repeat infinitely many more times. If we were to keep on plotting the sine wave, we would just have more of those same parts. So this is the picture you would replicate over and over again to get a full view of cosecant, or just a wider view. So just to emphasize that, here's y equals cosecant x, and it's just a whole bunch of pieces like we just drew over there. Loads of them, but we're just doing this over one complete period, so we just see the 2 parts of the graph here. It does tell us right away that the period is 2 pi, so that's important information. It retains the same period as the sine curve. Another important fact about this when we go to plot is the first point you're going to plot is always going to be a vertical asymptote each and every time. The next point is either going to be a max or a min within the vertical asymptote each and every time. If this was negative sine, it would have been flipped across the x-axis. So this is the base curve. Your third point is automatically going to lead to your vertical asymptote, the next part of the graph we want. Fourth point, either the minimum or the maximum between the asymptotes, this time a minimum. And the fifth point is the final vertical asymptote. So we'll always draw 3 vertical asymptotes and then a curve in between the 2. So that's kind of cool in a way. For your plot to show all of these features, you have to also be using the fact that the increment, so where it just keeps on coming back, is 1/4 of the period, which is equal to, in this problem, pi over 2. But the fundamental formula is this right here. If we change the period, if we stretch it or compress it, it's still going to be 1/4 of the period. The number over here just changes. We'll always, on every single graph, start in this 1, 2, 3, 4, 5 process using 5 base points on the sine wave to get our cosecant graph. So that's how each one of them is going to come together. Any questions at all, folks, before we try out our first? Okay, so here's the next one. This one is the one that would look like an actual homework problem. For each of the function, do the following. State the period and the phase shift. It didn't ask us to state the amplitude because there is no amplitude. Those vertical asymptotes means there's no ending to where this goes up. There's no bound there. There's no ending to how this goes down. There's no lower bound. So no amplitude whatsoever on this curve. Still, the period and phase shift is useful, so that's a good place to start. So for period, I'll put this one in blue. The formula for sine would have went 2 pi. Actually, let me put it in black and use color coding slightly differently. Period would have been 2 pi, divide by whatever goes here. That's what we would have done if we were plotting the sine wave, and the instructions are exactly the same so far. So that part is a really nice and direct carryover. That portion there is just a division, and the period is 1. So we're still plotting the same curve as above, but it's been stretched in different directions and it's been phase shifted. This part right here is going to give us the phase shift where it's located on the x-axis. So like before, I'll write PS to stand for the phase shift. Whatever the sign here is, we take the opposite like we mentioned in the last notes. So for a positive pi, we'll go negative pi. That 2 pi factor in front still divides just like before. And so the phase shift is just negative 1/2 altogether. Well, so far, we look at the notes from the Canvas website on the summary applied techniques. By the way, I moved it down to the 6.2 section just to make it more readily available. We really didn't change the formulas at all. We still use the same formula for period, same formula for the phase shift. And now we want to do the cycle start, find out where it ends, and begin plotting the cosecant function. Maybe before doing all that, the magical value that tells us where the asymptotes are and are the maximums and minimums within the asymptotes are based off this formula, the increment. Increment in this, even if it's a cosecant, is exactly the same. It is 1/4 whatever the period came out as. So that's a nice, again, direct carryover. This will be 1/4 times 1. So that's just 1/4 altogether for the increment in this plot. From here, we could just start plotting, but it's a good idea to also say, where does it start? Where does it end? So I'll put here, start is going to be equal to the phase shift, which was negative 1/2. Then it's going to end at wherever it started, negative 1/2, plus the period. So this will be negative 1/2 plus, by the red dot, the period is 1. But we can make that a 2/2 for a 1/2 altogether. So our plot starts at negative 1/2, it ends at positive 1/2. We're incrementing by 1/4. Not the most compatible fractions, but if it helps, you could rewrite these as negative 2/4, positive 2/4, and this gets us started. Well, this is the rundown we would have done in the very last section, except I don't have amplitude. That's really the only thing missing. We didn't say anything about the midline. From here on out, we would have immediately drawn a line that goes like this. Let's see, my start and my end is symmetric, so I'm going to kind of give equal weight to quadrants 1, 2, 3, and 4. Let's put the axes right down in the middle. One other thing we need to do, though, is we don't just need to set the horizontal axis. We also need to set the vertical axis. But that's not too bad. Whatever the amplitude is for the sine wave tells us what the scale is. So this will be, I'll put it about here, height 2, height -2, just coming from whatever's in front of the function. If that was a -10, I would have went positive 10, -10. And if it was a -10, I would just have to be mindful that the sine wave in green flips around, and so does the cosecant wave in blue. So we're about ready to start plotting. We just need to put down some tick marks. Starting at -2/4, so let me go 1, 2. So here's -2/4 or -1/4. Totally up to you how you'd like to plot these or simplify them. Negative 1/4 here, then we're off to 0, positive 1/4, and then 2/4. So we have 5 points. There's just the tick mark here is overwritten by the y-axis. And the new thing about the cosecant wave is we have vertical asymptotes. But this is all the setup so far. And if we were just plotting sine, we would have taken these exact same steps. Any questions at all, folks, to this stage? Okay, so we've got the period, the phase shift. We're going to plot over one full period. But on the x-axis, we have to label the positions of the vertical asymptotes using dashed lines and mark the exact values. We already did this part. We labeled the y-axis to indicate its scale. See the yellow color coding for how we did that. And key fact about cosecant, when we plot this over one period, the plot will start on vertical asymptote. So this pattern is going to happen for every single one of these. We're going to have a point either above or below. We'll see what's happening with the whole function here if it were a sine wave. But then the next one is going to be a vertical asymptote. So they're alternating in this way. Another point either above or below. Last point, vertical asymptote. So no matter what the transformation is on cosecant, there's always going to be these three vertical asymptotes on the fringes, one in the direct middle. The next thing you might jot or think in your mind, if it was y equals a sine x, we would have plotted something that goes like this. Sine wave with a positive coefficient in front starts on the x-axis, increases, decreases, and then increases again on that way. So finally, that tells us that this curve, well, it started on the x-axis. That's why there's a vertical asymptote. Sine increases to this point. I don't want to plot the whole sine wave because it'll be distracting what our answer is. We're just plotting the actual point, which would have been right up there. Then when we go to here, that's at this point. That's why there's a vertical asymptote. When we go to 1/4, that's this point. So we're at that highest point here between the asymptotes. And then over here, that's just the vertical asymptote coming from the sine wave. From here on out, all we need to do is plot those curves. It's always going to be repelled away from the horizontal axis. So it's going to shoot up like this. It's not quite a parabola, but it might look like one, across really short ranges. Parabola would go to the right forever, but it's blocked by this boundary, the vertical asymptote. On the other side, just draw a symmetric picture of it. It's just flipped, move to the right. And so it'll look like that. So that's our plot for 2 cosecant 2 pi x plus pi. Interesting transformation. And really, it's just kind of a redo of the sine wave. Again, if we apply the sine wave, it would have looked like this. But we usually want to leave that off. It's more of just a guideline. So usually we think of the first point as the vertical asymptote, and then just draw these points and these points to get the rest of the curve, or the cosecant curve. But that's one down. Plotting sine and cosecant are kind of fun in a way because they go together so well. For the information on sine, if we extend it down to cosecant, notice there's not a lot of difference, aside from the amplitude is undefined as the major thing. But the rest of the cookbook for plotting it is essentially the same stuff as you see right above. It's nice to see the parallelism there. If you're a person that likes looking for patterns and seeing these differences, that's the stuff that's highlighted or in the red text. The things that are different amongst the patterns are also the things that are in yellow highlighting, in bold, and in red. Secant is a really unusual one to plot, as you can tell from the notes right here. So that's going to be our next one to tackle. To get a plot for secant, really we're just going to redo what we did in the notes and start by plotting sine and see how it relates to secant. Excuse me, start plotting cosine and see how it relates to secant. So here's kind of like the warm-up problem to that. We'll think of cosine in green, secant in blue. And really the notes could have just started right here and they would have looked similar, but there's one thing that's a little bit weirder about secant. We'll see in just a moment. When we write out what secant is, in terms of cosine, it goes 1 over cosine x. So far, so good. Nothing too different from example 1. We want to get our vertical asymptotes going, so we'll say that secant x has vertical asymptotes where cosine x is 0. But that's at different spots than sine. Cosine x goes to 0 at pi over 2 when you're at 90-degree rotation, then again at 3 pi over 2, or the positive and negative versions of them. So cosine x equals 0 implies x equals positive or negative pi over 2, positive or negative 3 pi over 2, positive or negative 5 pi over 2, and so on. That's the pattern for all of the vertical asymptotes where cosine x is 0. It's this time odd multiples of pi. There's no 2 pi over 2. That would have been pi, and cosine pi is -1. So it goes 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2 if I had extra space, and so on forever. Positive and negative makes sense because, well, cosine's an even function. Cosine at negative pi over 2 is cosine pi over 2. There's no difference there. This allows us to get started with what the sketch should look like. This time I'm going to move the axis a little bit more to the right. This curve up here has amplitude 1 for cosine, so that means put in a positive 1, -1 on the vertical axis. And the comment we made before when we were plotting cosecant is relative here. We want our plot to start on a vertical asymptote and end on a vertical asymptote. So we'll need to do that for full credit on the secant plot as well. And that's why these plots are a little bit more challenging to get started, get everything in the right spot. The first vertical asymptote we're going to plot is at negative pi over 2. So let's put that one down. So it'll be negative pi over 2 slightly to the left. The next one is going to be at positive pi over 2. Then we move over. The last vertical asymptote is going to be at 3 pi over 2. And I have slight regrets on how I'm plotting this. Let me put in a little bit more space. So I went from negative pi over 2 to 0 to pi over 2. Then, let's see here. Let's put in pi, that's the better unit length there, or 2 pi over 2. Then this will be 3 pi over 2. That's the better way to plot all this. Okay, that looks a little bit more accurate this time. Let me try to make these a little bit smaller so we can plot the curve on there nicely. And if we went a little bit further, we usually end the plot at 2 pi. So let's do that just so we can reference how the old cosine curve is going to be plotted and how the new one will be plotted. Ordinarily, for plotting cosine, we start right here, right at the maximum. Then cosine pi over 2 is 0. Cosine pi is -1. Cosine 3 pi over 2 is 0. And cosine at 2 pi is back to +1. And this is what our cosine wave looked like when we plotted it. A nice gentle curve that does something about like that. However, we want to start at the vertical asymptote, so we're actually going backwards down to this point. This is still our y equals cosine curve, but we have a little bit more than we didn't actually need because we went backwards by, well, the period is pi over 2. So 1/4 of the period is, or excuse me, the period is 2 pi, getting my thoughts combined. Period is 2 pi, so 1/4 of the period is pi over 2, and we went left by pi over 2 to get here. Reason we did that is we're starting on a vertical asymptote. That's where cosine goes to 0. We have a maximum value. Then here we have another vertical asymptote at positive pi over 2. We have a minimum value that's going to tell us where to plot the secant curve. And the final vertical asymptote at 3 pi over 2. And this is going to be the start. We'll write down a formula for that. And this will be the end. So that means we didn't need this excess at all, but we'll leave it on the plot just to emphasize we actually went backwards a little bit to get a good plot on secant. And from this point on, it's just like you're plotting cosecant. Cosine at 0 is 1, so secant at 0 is also 1. Secant curve is repelled away, goes up in this direction on both sides of that point when x is 0. Then when x is pi, to the left and to the right, it's shooting downwards. Values are becoming extremely large negative very quickly. The closer and closer we get to the vertical asymptote. So this curve here is y equals secant x. It's unusual, and this is where this part of the notes comes in. The start of this is going to be negative 1/4 of the period. That's the negative pi over 2 you see right here, plus whatever phase shift happens to be in this problem. This one had phase shift of 0, so that wasn't as important. But the start is negative 1/4 of the period. So the increment, by going backwards, so we can hit the vertical asymptote here, plus the phase shift. Let's hide that yellow because that's the first part of the notes, I would say, that is pretty tricky, this bit right here. So we'll make a really big deal out of it when we go to plot for the first time. It is all having to do with that vertical asymptote there and 1/4 of the period being pi over 2. We had to go backwards to hit the vertical asymptote is the short of it, leading to this formula here. Well, any questions at all, folks, with our quick plot of the secant function? Okay, same really quick facts, just like with the cosecant. This function has period 2 pi. That's the distance from here all the way to here is the distance 2 pi. Amplitude is undefined on this one. And the increment is going to be 1/4 of the period. So whatever the period happens to be, this is like the special value getting us the intercepts, maximum within intercepts, and so on. So here's the next run. We're plotting this thing, negative 5 secant 3 pi x minus pi over 2. It looks like a lot of stuff, but same exact instructions as before. The major thing we just have to be aware of is where the plot even starts. So the cycle starts here. Well, we'll go down the line of the typical information that you're probably expecting at this point. We've done them all essentially the same. We want a period. The period we write inherits the period from cosine. Secant and cosine have the same. It's going to be 2 pi. But then anything multiplying here is going to shrink or compress. Said that backwards. It's going to compress or shrink. I think I said that possibly backwards as well, but you get the idea. By that factor. So 3 pi goes down here. And now the period is 2/3. So we went from a period of 2 pi, 6.28 roughly, to just 2/3, 0.6 repeating. It got compressed a whole bunch by putting in that 3 pi in front of x. Then this thing, don't forget the sign is important as well, is also going to relocate it. It's moving it to the right, but not by pi over 2 because 3 pi influences it as well. So we take as the phase shift. First, flip the sign. That's the most important thing to remember. It's going to be positive pi over 2. Then we divide by this factor here also in fact influences how things are relocated. So it's pi over 2 divided by 3 pi. Here we'll just do some fast arithmetic. This is pi over 2 times 1/3 pi, flip the denominator. So this becomes 1/6 after cancellation. Have a nice cancellation there, losing the pi. Same with the cancellation here. So we have the period, the phase shift. I would probably, as an immediate next thing to do, is get the increment in. The increment has a really special role this time because we need the increment to know even where it starts. Does not start at the phase shift, or else we're going to have a really weird plot because the first point you put down is not the vertical asymptote at all. So this thing, 1/4 the period, we calculate first. Increment is what we've been calling it for the sake of parallelism and maintaining that pattern. Let's continue to do so. 1/4 of the period, which is going to be 1/4. Look up for the period. That one was a 2/3. This one also reduces a bit. This becomes a 1/6, which is kind of nice. It's compatible with the phase shift. So the increment is 1/6. That means the cycle start, or the period start, I'll just simply call it start. This deserves some, well, I want to use yellow for something else. This deserves color coding for sure, because this is probably one of the trickiest part about plotting the trig functions. The start is negative 1/4 of the period. Notice we've already calculated 1/4 of the period. So we're just putting a negative sign in front of that, plus the phase shift. And really, that's exactly what we did over here. Here, the start was negative 1/4 of the period. It just so happened the phase shift was 0. We're starting that way so we can line up the very first vertical asymptote. Now we can make some substitutions. This negative 1/4 of the period plugs in a negative in front of a 6th. Plus the phase shift, the next substitution we have on the left is 1/6. So it starts at 0. We're just about there. This probably deserves some of this. I'm not sure what color that is. It's salmon, color coding as well, just for emphasis. Then the end on this is going to be whatever you said your starting was, 0, plus the phase shift, or excuse me, plus the period. 2/3 tells us how long the run is to get one period. So that's the ending position. Right at 2/3. Looks like everything is in 6th, though, thanks to that increment. So to make it easy on the eyes as you plot, you can convert this to 4/6 as well, if you prefer. Well, this gets us started, and we're now ready to write down a horizontal axis and then a vertical axis next. Any questions with any of this information we put down? Okay, so let's start off. Because we're starting at 0, really all we want is quadrants 1 and 4 in our plot, so we'll emphasize those. I'll try again on that axis. A little better. Then for the horizontal axis, it goes pretty quick. That number there, which would have been the amplitude for the cosine, tells us the scale on the vertical axis. So y-axis will have a 5 here and a -5 down here. Then, well, our first tick mark is right at 0, and that's automatically a vertical asymptote, just like with the cosecant function. Then we have another point at 1/6, another point at 2/6, but these alternate. The third point is also a vertical asymptote. This is the middle point as well, and we'll always have a vertical asymptote directly in the middle. Then it's 3/6. Finally, 4/6, ending on the last vertical asymptote. So we've started at 0, we've ended at 4/6. We now have a whole scale set up for the horizontal and vertical direction. All we have to do is plot this thing, and the next major danger is watch out for the negative sign. It's going to flip our graph on us. So next things you might want to jot down in your mental chalkboard, or maybe just on the margin of the paper, is if you're plotting y equals cosine x, it would have looked like this. Starts at the maximum, dips down, returns to the maximum. But what we're thinking of is a negative cosine x. So the next plot that we want to really focus on would actually start at the minimum, increases to its maximum, then returns down to its minimum. So the negative causes a reflection about the y-axis. And this is the curve we want to pay attention to as we plot. So moving left to right, we have a vertical asymptote. Oh, hang on. One thing that's a little tricky about this that trips me up is, recall also, we moved cosine to the left by 1/4 period. Let's review why we do that. So we can actually start on a vertical asymptote. So that's the new thing that's confusing about the secant plot. Secant and cotangent are the only two that have this feature. Everything else is a little bit nicer. So back over here, you have to move over a little bit more to that spot, and then you have the actual points we're going to use. So now going left to right, vertical asymptote here, it's because we moved to the left by 1/4 period on the cosine, and it's negative. On this one, we should be hitting a minimum value for that second point. So here it is, kind of a larger point on our plot. Vertical asymptote came from where this point would have been. 3/6 comes from its maximum. And sure, we're just looking at negative cosine x without all the fancy transformation stuff. But this is just a guide because those points emerge in the same order, no matter how you stretch it or compress it. So over here, 3/6, we have that point there. Finally, at 4/6, that corresponds to this one. Oh, skipped one. To this one, where a vertical asymptote would have emerged. Really, once we have these 2 points, our job is done. The curve will never intersect the x-axis. It's repelled away. So it goes like this. And in the next window, between the asymptotes 2/6, 4/6, it goes upwards. And now we've handled the negative sign by just taking this curve and then remembering to go left by 1/4 period and just flipping the whole thing. So that's our plot for -5 secant 3 pi x minus pi over 2. Takes a lot of oxygen to say, but those are the steps in plotting this thing. Any questions whatsoever, folks, doing this plot here? Okay, I think this is a good one to pause just for a moment and reflect. What do we want out of this algebraically? When we're in chapter 7, we're going to be doing the next big part of this, the course's objective of solving trigonometric equations. We mentioned this before, but a follow-up question to this could be, how many solutions does -5 secant 3 pi x minus pi over 2 have between 0 less than or equals to x less than or equals to 4/6, or 2/3 if we reduce that. Let's reduce it here. I usually leave it unreduced on the horizontal axis just for ease of getting these points down. So, oh, and I didn't write an equation. Let's say equals 6. So we can see just from a glance, if we go to height 6, there's 2 solutions. So that would be our answer, 2 solutions. The way this helps us is, we're trying to solve equations like these. Let me move over the word have. That looks weird now. When we go to try to solve these kinds of equations, it's good to know how many solutions to expect in the first place. And so citing the graph and then finding those solutions algebraically, getting their exact values, you'll know the minute you get 2 solutions, your job is done and you can just stop right at that point. So that's one way we can think about the use for these plotting these things. We'll see other reasons for plotting functions like sine, cosine, secant, and so on when we go into the section 6.3. where the big goal there is to define the inverse functions as well. And finding inverse functions means you have to pass a so-called horizontal line test. So that'll be the next interesting thing we'll be getting into. But any questions at all, folks, with the conclusion on example 4 or the related comments? Okay, so we've navigated through, not that, but this tricky part right here, dealing with secant. Now, if we want to extend the notes, last two things are going to be tangent and cotangent. We'll do tangent next, since it seems to follow in a nice flow. But notice the problems with tangent. Tangent is sine divided by cosine, and secant was 1 over cosine. Anytime you have cosine in the denominator, the position you start your cycle in is just a little bit off. So these are the only two weird functions when it comes to starting off your plots. So let's turn next to the tangent function, see what this one's all about. We want to, on these instructions, plot y equals tangent x over 2 full periods. So this is new right here. This will be mentioned as well in the homework problems and the problems we do on the notes. We're suddenly going for 2 periods. And that's just to give some parallelism and a good feel for the graph. There's actually not a lot of points if we did just 1 period. First thing we want to do is analyze the tangent function. Y equals tangent x. Let's put that in blue like we did before. So y equals tangent x, if we want to redefine it, is just saying take the sine function, divide by the cosine function. The numerator is not going to give us anything in terms of asymptotes, but the denominator will lead us to vertical asymptotes, just like when we were dealing with the secant function. So we can say that y equals tangent x has vertical asymptotes when the function of the denominator, cosine x, equals 0. And this will be at same deal with dealing with secant. This will be when x is equal to positive or negative pi over 2, positive or negative 3 pi over 2, positive or negative 5 pi over 2, and so on. I never seem to write enough space for 7 pi over 2. Let's get the plot started. So for plotting tangent, first thing we'd really do is begin with the vertical asymptotes. So we'll put down a long horizontal axis. Because we're going to start at a negative pi over 2, I'll put the vertical axis kind of a third to the right. Maybe not that big. That should do the job for us. Then right away, we'll have a vertical asymptote at negative pi over 2. At this position right here, we're at 0. But that's not so bad, because if you're at 0, you could just simply say tangent at 0, that's going to be sine at 0 divided by cosine at 0. But sine at 0 is 0, cosine at 0 is 1, so this whole thing is 0. That's nice because it gives us a point right here. We've got infinitely many to go, but there's 1 point already for the tangent curve. Then we go over to pi over 2. Tangent at pi over 2 is undefined due to cosine pi over 2 being 0. That just means another vertical asymptote. Then it's going to be 2 pi over 2, which is just pi. Tangent at pi is just like sine at, or tangent at 0. We would take sine pi, which is 0, divided by cosine pi, which is negative 1. But the whole thing is 0, so we've got another x-intercept right here for the tangent curve. Go another distance, 3 pi over 2, and we get another vertical asymptote. So this is the tangent curve so far. In fact, one cycle is just from here to here. The period is just pi, actually. That's why we're doing 2 full periods, so we have more impressive plot. It also gives us 5 points, so it makes it feel very similar to what you're doing on your last plots as well. We just have to know, what does the curve actually look like when we go to plot? Vertical asymptotes really help us out because the curve is going to be attracted to the vertical asymptote. The question you might have is, does it go down if we're reading from the center, the origin, going to the left? Or does it go up? Likewise, you might wonder, does it go here or here? Until we resolve that, it's kind of a mystery on how to plot it. But there's a number of ways to get a feel for this. You could just compute more tangent values. We'll do exactly that. Right here at this position would be pi over 4. So if we calculate, let me scroll down for a bit for room. Tangent pi over 4, well, that's just like we see here, sine divided by cosine at that angle. But sine of pi over 4 and cosine pi over 4 match. They're both root 2 over 2. And so they're equal to 1. So if you go midway between an intercept and the vertical asymptote, you get a point here that's 1. And we're going to replicate this strategy because it turns out that's how you set your vertical asymptote. You can just literally put a tick mark right in the middle, go up by whatever number is in front of tangent. If that was 5 tangent x, we would have just put a 5 down right there. It's kind of a cool trick, and it also tells us moving from the intercept to the right, the tangent curve is going up like this. So questions we might have is, does it look like a secant or a cosecant? Turns out it's a no, it goes down this way. That's because if you go to this spot, this is negative pi over 4. Tangent at negative pi over 4 is much like this right here, except at negative pi over 4, here's the new situation. We're over here. The cosine value for the denominator is going to be positive root 2 over 2. Sine value for the numerator is negative root 2 over 2. So this one becomes a negative 1. So down here, at negative 1, we have another point that goes into this location. The rest of the plotting is automatic because once again, the tangent curve is attracted to the vertical asymptote. So the plot looks like this. That's kind of an ugly plot. Let me try to do it as one nice, smooth, connected curve. It's increasing as you go left to right. That's one cycle going left to right here. We're doing 2 cycles or 2 periods, so we just try our best to duplicate that same graph. Here it is the second time over. And we've got it, folks. This is y equals tangent x. It's a pretty interesting curve. It says something about how we might try to invert it later. But key facts about this is that the period is 2 pi, and the start is again slightly different, negative 1/2 the period plus the phase shift. Why is it negative 1/2 the period? Because we started, the period is, oh, that's a mistake there. If the period is pi, I feel like I need to emphasize that after that mistake. The period is pi, the distance here to here. Then pi over 2 is half the period, and that's where we started, right at negative pi over 2. So that's why we see here on the plotting technique summary, we start at negative p over 2, whatever the period might happen to be, then add the phase shift. So we'll practice plotting this curve again, and then the cotangent curve next when we come back on Wednesday's class. But any questions or comments at all, folks, on the rundown for dealing with tangent? Okay, looks like we're nearly done with the plotting techniques. Pretty much it all really just depends on knowing how to plot sine cosine really well. And then other new information for tangent cotangent are the next pretty big new elements. So we'll practice this on Wednesday's class and probably take a look into section 6.3 as well. But have a great night, folks. We'll be back to this again on Wednesday. Take care. Yep, you betcha. Yeah, I hear you. I'm not honestly. I took a psychology class once where someone had to nudge me on the shoulder because I was in fact snoring at that point. I just saw that, Chen. Well, you can always take a look into the video once it's posted, and no worries if you have questions on it. Oh, that sucks. Sorry about that. You bet. Good luck on the test. Thanks, you too. Take care.